In this video, I'm going to go over the answers to classwork 6. So part A says, consider the utility function u x1, x2, x1 to the 0.5 times x2 to the 0.5. This is a monotonic transformation of the u x1, x2, x1 times x2 utility function that we've explored a couple of times. So indifference curves are the well-behaved ones we're used to seeing. That is, they look like these nice C's. Taking another monotonic transformation, the natural log, to see that u of x1, x2 is 0.5 ln x1 plus 0.5 ln x2. I'll do this to make u easier to work with. If the optimal bundle is an interior point, then we have two equations. The marginal rate of substitution is equal to the budget line. The slope of the budget line, where the marginal rate of substitution is the slope of the indifference curve. We learned last chapter that the marginal rate of substitution is the negative of the partial derivative of u with respect to x1 divided by the partial derivative of u with respect to x2. And then our second equation is that the budget constraint must hold at an equality. We're going to spend all our money. P1x1 plus P2x2 equals m. Suppose P1 is 1, P2 is 2, and income m is 5. We also have two unknowns, x1 and x2. We're going to solve for these two equations and two unknowns. We should get x1 is 2.5 and x2 is 2.5. So let's start working with the first equation here. We have that the negative partial derivative of u with respect to x1 divided by the partial of u with respect to x2 should be equal to negative p1 over p2. What is u here? We're going to work with this version. That's the easier to work with one. So what's the partial derivative of this with respect to x1? This is a constant, so we'd ignore it. We'd have 0.5 times 1 over x1 divide by the partial of this with respect to x2. Same thing, but with x2, 0.5 times 1 over x2. That's going to be equal to, and then there's negative out in front. That's going to be equal to negative P1 over P2, which in this case, I tell you that P1 is 1, P2 is 1, so that'll be negative 1. I'm going to cancel the negative signs from both sides, and then I'm going to simplify this a little bit. Also, I'm going to cancel, so you see I have 0.5 in the numerator and the denominator here. I'm going to cancel that 0.5. So then we'll have 1 over x1 is equal to 1 over x2. And then I can cross multiply, I guess. I'll end up with x1 equals x2. Now we're going to, so we've just been working on this first equation. Now I'm going to make use of the second equation right here, our budget constraint. So our budget constraint says, remember that P1 is 1 and P2 is 1. Budget constraint is x1 plus x2 equals the income 5. And I'm going to substitute in what we learned from this first equation, which is that x1 is equal to x2. So I'll get x2 plus x2 equals 5. And now I have one unknown, 2x2 equals 5, and x2 is 2.5. Then I can come back here, knowing that x1 equals x2. They're both equal to 2.5, which is what we wanted to show. 2.5. Okay, so that's part A. Going down to part B. It says, a utility function from part A that's of the form u x1, x2 is x1 to the a times x2 to the b, where a and b are non-negative and a plus b equals 1. Remember we had a and b were both 0.5 here, so they sum to 1. That utility function is called a Cobb-Douglas utility function. It has a useful property where the exponents a and b tell you the share of the income that will be spent on goods 1 and 2 at the optimal bundle. For instance, in part A, the exponents were 0.5, 0.5, and you showed that when prices were equal, we bought equal amounts of good 1 and good 2. Write a proof of the fact that if utility is Cobb-Douglas, then you'll spend A of your income on good 1 and B of your income on good 2. Okay, so we want to show that we're going to spend A of our income on good 1 and B of our income on good 2. So M is our total income. And if we spend A of our income on good 1, then that means M times A will be the expenditure on good 1, and we divide that by P1, that should equal X1 star. I guess another way to see this is if MA is our expenditure on good 1, X1 star P1 will also be the expenditure on good 1. So we can divide both sides by P1 to see that X1 star should be equal to MA over P1. Likewise, we want to show that MB divided by P2 is X2 star. That is, we're going to spend MB that's our expenditure on good 2, which is otherwise known as X2 times P2. All right, so let's get started. You may be kind of confused about where to start with this problem. The hint is it's going to progress exactly like part A was. We're going to have 2 equations and 2 unknowns, and we're going to solve for them, hopefully showing this by the end. But we're not going to, so here we got X1, this should have been stars too. X1 star and X2 stars is 2.5. This time we're going to figure out what X1 and X2 star is, but we're going to kind of keep it more in the abstract. We're not going to put numbers down here for M, A, P. All right, so we start with this marginal rate of substitution equals negative P1 over P2. So we're starting here. The marginal rate of substitution equals negative P1 over P2. The marginal rate of substitution is the partial derivative of u with respect to x1, negative, divided by the partial derivative of u with respect to x2. And the dog needs to get let out, so I'll be right back. Okay, I'm back. So what is the partial with respect to x1 here? I'm going to take this, and I'm going to take the natural log. That's a monotonic transformation that just helps it be easier to work with. So we have that u, x1, x2 is a natural log x1 plus b natural log of x2. So take the partial derivative with respect to x1 to see that we have negative a over x1 divided by b over x2. That's going to be equal to negative P1 over P2. So that's our first equation. Our second equation, I'll label that equation 1. Our second equation is the budget constraint, which is just P1 times x1 plus P2 times x2 is equal to M. We spend all our money. And so that's equation 2. And the idea is we want to take our 2 equations and solve for our 2 unknowns, x1 star and x2 star. And by the way, when these equations hold, we're no longer talking about just any amount of good 1 and good 2. We're talking about x1 star amounts of good 1 and x2 star amounts of good 2. So when those equations hold, we can be talking about the optimal bundle. So I'm going to combine these equations, maybe simplify a little bit, and then we'll see where we're at. So maybe I'll start simplifying from here. A lot of different ways you can do this. I'm going to cancel the negative signs. Get a over x1 star is P1 over P2 times B over X2 star. Let me multiply this both sides and then also this to both sides. So I'll get A P2 X2 star is B P1 X1 star. And now, see, so I have a P2 X2 over here. So I want to solve for P2 X2, I think. I have that P2 X2 star is B P1 X1 star over A. Now I can put it in, the equation, finally combine the two equations here. So I have P1 X1 star plus this thing, B P1 X1 star over A equals M. Now I finally have one equation and one unknown. I just have X1 star to solve for. So let's solve for X1 star. Let's see, I have a P1 X1 star 1 plus what's B over A equals M. I want to combine this to be, I want to find common denominators so that I can have one term here. So to make common denominators, I'll show that 1 is just A over A, right? A over A plus B over A, P1 X1 star. And now I can add the two. P1 X1 star is A plus B over A equal M. And then I will solve for X1 star. So X1 star is M divided by P1 times the reciprocal of this, which is A over A plus B. And remember, in our assumptions for Cobb-Douglas, we said that A plus B equals 1. So this thing is 1. And so we have X1 star is MA over P1. And that should have been, I think that's what we wanted to show. Let's check. X1 star is MA over P1. Yeah, we got it. Now let's work on showing that this is true. Let's go back to solve for X2 star. So we have this for X1 star. Let's go back to our budget constraint and put that in for X1 star to solve for X2 star. So we're going to have P1 X1 star, which is MA over P1, plus P2 X2 star equals M. The P1s cancel here. So we get P2 X2 star is M minus MA. I'm going to collect M over here to get M, 1 minus A. And I'll divide both sides by P2. So I get X2 star is M, 1 minus A over P2. That's not exactly what we wanted to show. We wanted to show that X2 star is MB over P2. But notice, if A plus B equals 1, which is our assumption, then 1 minus A is equal to B. So these things are equal. And I think that that's all we needed to show here. Let me go check. Yeah, exactly. All right, part B is done. All right, let's move on to part C. Part C says, suppose that we observed a consumer's choices at several prices and income levels, see the table below. S1 and S2 are the shares of the consumer's income spent on goods 1 and good 2. So let's look at the data. So we have years 1, 2, 3, and 4. Over the course of these 4 years, price 1 and price 2 fluctuated a little bit. The income of the person fluctuated a little bit. and we see the person buying different amounts of good 1 and good 2. And then you can calculate the share of good 1 and good 2 as a function of the person's income, like this. The share should be M divided by, the expenditure on good 1, which is P1X1, divided by the total income M. And share of expenditure on good 2 should be P2X2 divided by M. So let's just check and make sure that makes sense. So here, P1 was 1, X1 is 25, so we'll get 25 in the numerator divided by M, which is 100, and then that's why we got a 0.25 here. So that's the share. So the data shows that the consumer's share of spending on goods 1 and goods 2 stays very stable at 0.25 and 0.75. So even though prices and income were changing, we saw the share of good 1 staying stable at just around 0.25, and the share of spending on good 2 hovering just around 0.75. So an economist might very well choose the Cobb-Douglas utility function, because it's an excellent choice to model this consumer's preferences, because however prices and income are changing, we see the shares staying constant, and that's exactly what happens with Cobb-Douglas. Add another column U that calculates the consumer's utility during each year. So adding another column U here. We're just gonna stick the X1 and X2, so this, into the utility function, which is this. So the utility for year 1 would be the utility of getting 25 and 75 of goods 1 and goods 2, which is 25 to the 0.25 times 75 to the 0.75. And so you can get out your calculator, work on that, or you can use R. This is kind of a fancy way to solve a problem. I define a function that has 2 arguments, x1 and x2, and it returns x1 to the 0.25 times x2 to the 0.75. So I can kind of quickly solve the whole problem by putting in 25 and 75 into my function. So I get a utility for year 1 of 57. Then a utility for year 2 of 33.9. Utility for year 3 of 47.9. And utility for year 4 of 67.8. All right, so that's the first part of the problem. We can use this model of the consumer's preferences to evaluate the impact of proposed policy changes, that is to do counterfactual analysis. Suppose that, for example, that the government is contemplating imposing a system of taxes that would result in prices 2-3, that's for good 1 and good 2, and the consumer having income 200. How much of goods 1 and goods 2 would the consumer choose to purchase, and what would their utility be? Would they be better or worse off compared to the years in the data? So first we want to solve for x1 star and x2 star here. We know that their utility is Cobb-Douglas, so we can use the formulas that we solved for here. We know that, let's see, where is it? X1 star will be this, and x2 star will be, the same thing, but for B and P2. X1 star is M, which we said is 200 here, times the coefficient for X1, which is 0.25, divided by the price of good 1, which was 2. So that comes out to be, let's see, this will be 100. A quarter of 100 is 25. And then x2 star will be MB over P2, which is 200 times 0.75 divided by P2, which is 3 here. And what is that? 50. Yeah, seems about right. Okay. So we get that the consumer, under this new income and under these new prices, the consumer will buy 25 units of good 1 and 50 units of good 2. And if we stick that into the utility function from here, utility 25, 50, we'll see that the consumer is now left with 42.04 units of utility. And that has relevance because we can compare it to the utilities they experienced in different years. They were least happy in year 2. They were most happy in year 4. And under this new tax policy, they would be happier than they were in year 2, but less happy than they were in year 3. They'd be between these. So that's what I'm looking for you to say there. And then just finishing up, I'll read this last paragraph. Economists often analyze how a proposed policy might affect different groups of individuals, like teenagers, middle-class households, and the elderly. Each group has unique preferences for various goods, which are evident in their consumption and expenditure patterns. By estimating a utility function that describes these consumption patterns, economists can forecast demand and evaluate the potential impact of policy proposals. So hopefully you enjoyed that last problem. It's kind of cool.